Today we will discuss plastic analysis. You already know about the bending stresses in strength of materials 1. Okay, that's enough. Strength of materials, bending stresses. So now we will see what is plastic analysis. What is a plastic analysis? Just understand just it is. If it is an axial member. So what is the stress? Something. What is the capacity of the sectional area? What is the capacity of the sectional area? How much load we can apply? So are based on the material characteristics. What is the material characteristics? Material characteristics is the stress strain curve. Okay, stress strain curve of something, anything. If a concrete, steel, anything. So how much you can apply? Sir, we can apply it exactly at something. It is a failure. It is a failure point. It's a failure point, but we will take with up to yield point only. Factor of safety yield point only. So based on that, what is the yield stress? Something is yield stress something by Fy. So it has a yield stress. That material is yield stress F. Area is a. That is the strength. So if you applied more than that, we taken it as a failure. Failure of that section. That's it. That's it. That is the idea of what is a failure. It is axial member. Take same bending moment. Same bending member also. Same bending member. So it's a bending member. You can just take it as a bending member. So if you applied as something load is there, so reaction will come and a maximum bending moment will come like this. So maximum bending moment will apply. So how much load we can apply here? How much load you can apply? Where it is failed? So we have to encounter the bending strength of this cross section. That's it. Cross section. Cross section. Bending cross section. So how can you bending moment? Sir, bending stresses. Sir, it is a that section is yielding. That section is encountered the strain, sir. Encountered the strain. Encountered the strain. So later we will stress diagram also. It is a stress diagram. So mostly plastic analysis is applied for, not mostly, it's only applied for steel structures, not a concrete structures. We will discuss. Okay, only steel structures. Just strain will come, sir, later stress. So what is the maximum stress you can apply? You can apply it on that. So maximum is Fy. Maximum is Fy. So maximum is Fy. Later, so how moment is, sir? Moment is moment carrying capacity of that section. What is the moment carrying capacity of that section? M is F into Z, sir. So sectional model. Sectional modulus. Okay, sectional modulus. Section modulus. That is F into Z. So what is that F? F is only for yield stress based on the material characteristics. Material characteristics. So based on the material characteristics, we took the yield stress of that material F. So bending stress is F. If it is reach F, if it is crosses the F, we taken it as a failure. So what is the maximum moment we can apply for that section? Based on the cross F into Z. Z is BD cubed by 12. No, it's BD square by 6. It is a, this is I. It is a Z. I by Y is Z. Sectional modulus. You already know it. So for moment also same thing. So that is as elastic analysis. This is called elastic analysis. This is called elastic analysis. So what is the meaning of plastic analysis, sir? Plastic analysis. So everything you know up to this, you know it in a previous bending stresses. Bending stresses. Okay. So what is plastic analysis? So see, for discussing of the plastic analysis, we will first draw stress strain diagram for the mild steel. Okay, stress strain diagram of the mild steel. So stress strain. So how it is? It is up to a proportional limit. So later it is yield coming, upper yielding, lower yielding. lateral curve. That's it. So proportionality limit, upper yield point, lower yield point. So fracture point at the end. So you already know at the strength of materials, first class, first unit. Okay. So this is the stress strain diagram for mild steel. Mild steel only. Okay. So what is where is yield stress? Where is yield stress? Sir, this is a yield point. This is the yield point. This is a proportional limit. So we will take this is a Fy. That is a yield strain. Yield strain. So okay. So we will apply the stresses, forces on the material up to yield point only. We will take as yield point is a boundary. If you cross it yield point, we take it as a failure. We consider it as a failure, but reality it is a failure. No, I think you did a strength of metals experiment in a steel laboratory, but you didn't because COVID. Okay, if you encounter with a steel bar, if you apply a stress strain diagram, if you get a stress strain diagram of the steel, it goes like this: stress and the steel. Where it is really fracture, it's a failure at this point. This is a failure point. Otherwise, it's a fracture point. The steel bar gets a fracture at this location. Okay, but we just cross the yield stress, we taken as a failure. Why it is, sir? Why will taken as a elastic limit only? So if you cross the elastic point, permanent displacements are coming. If you cross the elastic limit, sir, what is the permanent displacements? Permanent displacements means, if you see, just see, if you applied a load, so at a certain proportionality limit, stress and strain are proportionality. So if you applied a load up to yield point, and you just release it, if you just a load, so this is a material. If you applied a load, so up to yield point, up to reaching the yield stress, applied a load and release it, if you get, what is happening? Just if you see, it's the material. If you applied a load, it will shrink like this. Strain, it will give strain. If you release it, you will get again the same shape. Up to elastic limit only. If you cross the elastic limit, so how can you get, sir? Just release it and again see the readings. The stress strain curve path follows the same path. If you release the load, it will follow the same path. There is no permanent displacements, permanent strains. There is no permanent strains. But if you cross the load applied here, and later you will release it, something like, if you applied load here up to layer and release it, regain the shape, but it has a permanent displacements. It won't regain its shape. The molecular displacements happening. Understood? So if you release it, it will follow the path like this. It will reach here. So it is a permanent displacements. So most of the loads will act certain time, later certain time. Maybe there is no constant load. Certain times maybe load is there, certain times you see in your classroom, all people come at morning 9, evening 5, they will leave it. So those are all temporary loads. They will come and go. So if you load coming, the permanent displacement is happening. Again some loading is happening. So again permanent loading is happening. Stress strains are altered because the length is changes. So area is altered. So stress strains are again altered. It will go collapse it. That's why they will limit up to the elastic point only. We limit the stress or strain also. So okay, that is the permanent displacements. So if you see, this is the diagram. So up to this we call it as a elastic range. These are all, you know it, elastic range. So again, up to this point, we call it as a ductile range. Ductile range. Ductile range means what? There is no increment of stress, but strain is increasing. Strain is increasing. So all understood? Strain is increasing. So again, this range is called, we can call it as strain hardening. Strain hardening. Strain hardening. At this place, molecular rearrangement is happening. Again, stress is small increment will happen. At, at this point is reaching, fracture will come, breakage will come. That is a stress strain curve of the mild steel. You have an idea about strength of metals first unit, first class. Okay, no need to discuss. So if you see, we will use only up to this much of energy only. Okay, we will use this much of energy. But in reality, if you take it as, there is no failure at Fy. There is no failure at Fy. The failure really happening this at this length. We wasted this much of energy, or we wasted this much of energy in the materials. This much of energy wasted in the materials. So if you consider that much of energy also, just consider. So in general, no buildings, no nothing structures will construct using plastic analysis. But any small such an example, certain examples, you will find out the examples, that is assignments, where the deflections are not a matter, only failure is a matter. Only failure is a matter, not a deflections, not a secondary movement, secondary stresses, strains, not a cancer. Just it have to be sustained. That's enough. That is the situations we will use that is. And also you can use it like a factor of safety. So this much of energy is there, this much of energy is there, we will obviously use this much of only. So we have a certain factor of safety. Are understood? So we have to find out what is the factor of safety. That is also for, to find out what is the ultimate strength. Just to find out the ultimate strength, that is the one concept. Just to find out what is ultimate, this is called ultimate, na? So you can call it as ultimate strength also. So what is the ultimate strength? What we are using. So what is the factor of safety? To find out what is the factor of safety also. That is just to find out, or somewhere we can use also. Sir, how can we use this much of energy also, sir? How it is using? So if you're using this much of energy, what is the capacity of that section? If you're using that much energy also, what is the capacity of the section? That is a plastic analysis. Okay, sir, understood? So now we will see, this is a real time stress strain curve. Real time stress strain curve. So idealized, what is idealized? So this is idealized stress strain curve for mild steel. Idealized. This is idealized. Okay, so small difference is small difference. This small difference is neglected. This is idealized. Idealized stress strain curve. Okay, so this is Fy, this is Xy, this is a failure strain. So for this is the stress strain curve for steel only, not a concrete. Okay, though we'll encounter in so next semester RCC. Okay, only steel, mild materials or elastic materials. So concrete is a, what is a concrete is a not elastic material. Okay, so only these are for the elastic materials. So okay, this is idealized stress strain curve. Okay, so now if you see, what will happen really, what will happen. So if anything, one section, if you say something, this is the section, if you applied a load for this section is encountered a moment na moment will encounter. So moment is coming that section. So it is what it is, it gets a deflection, it's getting deflection. Are understood? So most probably this is the maximum moment will have a chance. So what will happen in that section? what will happen that section? Just understand what will happen that section. Now you can understand. So maybe that section is rectangular or it's okay, taken as a I section. So just I section. Rectangular is most probably known as rectangle sections. Are you getting idea why? Mostly uses I sections only, not rectangular section. So that is the section if you feel it is. Just check it is. If you applied a load. So what will happen? The strains will come. Strain will come. That's it. Strain will come. Sir, how the strain will come? So how the strain will come? So exactly what will happen in this section? Just observe it. So if I apply a load, it will come like this. Now. The section will come like this. Are understood? So top sections are compressed. Bottom sections are expand. Are observe it? Top sections are compressed and bottom sections are expanding. So that is a stress curve. This is a compressed strain. So how much strain? This is the strain. Just see it is. That is the strain. That is the strain applied on section. So we taken as a uniformity. Okay. So that's why for this section also it will compress. The elements on that section is compressed. Okay. So bottom is expanding. So okay. Okay. So this is compressed. So what is that? This is theta. That is a curvature. How much it is? Based on that, this is a compressed. This is expansion. This is a strain curve. Okay. So based on that strain, we will go to the stress strain curve. For this strain, sir, this is the strain. For this strain, this is the stress. So for this strain, this is the stress. That's it. Huh? So how much we applied? How much we applied? Based on that, strains will come. Based on that strain, you will get to the stress. How much stress is? So most probably, see up to yield point, we will take in as a linear. So same thing. That's why stress diagram also come similarly. This is a strain. This is a stress. This is stress. Stress and strain. Are got the point? Stress and strain. So stress and strain. Later, how it is exactly if you applied a load, how it is not reproduce, how it is counterbalanced. If the certain force is applied on you, so 50 kilonewtons or something is force applied on you, how it is balanced, how it is reproduced. That's it. So if 50 kilonewton meter is applied on the section, 50 kilonewton meter is reproduced in the section, it will counterbalance. Okay, it will sustain. If the applied load is 100, your capacity is only 80, it fail. It is failed. So okay, just observe it. If you applied a 20, it will give 20. So otherwise, if it is just a table, just punch it. If you give per 10, it will reproduce it's a 10. If you give 20, it will give reproduce 20. If you this capacity of the table is only 80, if you applied 100, what will happen? It will break as. It will break as. That is a design philosophy you will get in RCC. Okay. So that's it. If you applied a 10, it will reproduce 10. So how it is reproduced? That is the idea. How it is reproduced? Based on the strains, it will give stress. Okay. Only stress and strains. Based on the stress, what is the force? If it is an axial members, this is a force. Fy into area will get force. So, but is a bending moment. How it is reproduce bending moment? How it is balance the bending moment? How it is counterbalance the bending moment? So, how it is balanced moment? So, these are the strain diagram. These are the stress diagram. So, exactly see, see, this is an exactly total area is in compression. This total area is in tension. So, total compressive force is something compressive force, total tension force is tension force. Exactly if you see, this is a lever arm, that is a lever arm. See exactly, we already discussed it. This is a C, this is T. So see, the movement is producing a, this is a lever arm. See the direction, if it is goes This is goes to this direction, this goes to this direction, it will produce moment. So that is exactly producing the opposite to the applied moment. It will balance it. So this is a compressive force, this is a tensile force, it will balance it. So up to what level? So it will apply 10, based on the 10 it has a strain, based on the 10 it has a stress. So based on the stress and strain, it will exactly give the equilibrium of compressive force should be equal to tensile force. Otherwise what will happen? It will move out. So exactly, it is a compressive force, it is a tensile force. Compressive force should be equal to tensile force, that is the equilibrium. Later, by these two forces has certain distance, lever arm, it will maintain lever arm, they produce a moment. That is the design philosophy, you will get more in RCC. Okay, so that is okay. So up to what limit? up to exactly up to exactly elastic limit. Okay, up to exactly elastic limit. So exactly at elastic strain, this is elastic strain. Okay, so this is elastic stress. Okay, this is elastic stress, it will reproduce exactly. This is the compressive force, this is the tensile force. So exactly what is moment? So compressive force or tensile force multiply with the lever arm. This is a bending stress, you already did, you got in bending stresses chapter. So that is exactly lever arm. So that is what, that is if you find out this compressive force, if you find out the tensile force, you will get it sigma into z, sigma y into z. This is called elastic modulus. This is called elastic modulus. So there is, sir, this has a formula m by I into sigma by y. So this is not a formula. So just check it, is just it's a multiplication of compressive force tensile force multiplied with lever arm. That is a reality. This is a reality, this is a formula. So otherwise, if you want proof, I will show you, just see, observe it. Take a rectangular section, take a rectangular section, take a rectangular section, it's a B, it's a total D. I will give a proof, small proof. So this is elastic stress. Okay, so it will reach us to elastic stress. So it is a compressive force, it is a see, so it is a compressive, see, it is a compressive force, it's a tensile force. Just see it. So what is the compressive force? This is the compressive force, that is the compressive force. What is the compressive force? What is compressive force? Sigma into of, that is the stress na. Sigma, it location is sigma, remaining location is varying from sigma to 0. So that is the sigma. What is the area? What is the area? So B multiply with d by 2. So B multiply with d by 2. That's it na? So what is that exactly? Sigma B d divided by 4. That is a compressive force. If you take a tensile force also, same thing. It is a rectangular section, we consider it. So, okay. So what is lever arm, sir? What is lever arm? What is lever arm? So lever arm is just, see, it is a triangular force. It is just a triangular force. It is just a triangular force. What is this? What is that? Exactly center of gravity. What is that place? It's a total is d by 2. It's a total is d by 2. What is this happening? 1/3 of d by 2. So remaining is 2/3 of d by 2. That's it. So this is a 2/3 of 2 by, this is a 2/3 of d by 2. This is also 2/3 of d by 2. Total is 4 by 3 d by 2. That's it. 4 by 3 d by 2. So total, see, movement is compression force or tensile force multiplied with lever arm. So you will guess sigma y b d by 4. Okay, multiply with distance is what? 4 by 3 of d by 2. 4 by 3 of d by 2. So that's it. So if you see, this is a compressive force, this is a tensile force, this is a distance. It will produce, so compulsory C, compulsory D. Otherwise it will slide over. Compulsory they should be maintain equilibrium. Throughout the section, at every point, every location should be maintained equilibrium. Otherwise, it is moving. Unbalanced force is there. So, what is moment? Force into distance. That is a moment. No? So, that's it. We write it. So, lever arm, you can call it as a lever arm. Okay. So, what is that value? See, it is sigma y b d square by 6. That is, we have to find out the moment carrying capacity of the section. The section carrying capacity is the section, this total section moment carrying capacity is, this is the value of the moment carrying capacity. Now you can see in the formulas you encountered like this, m is equal to sigma m by I into sigma by y. So m is equal to sigma I by y. Sir, I bd cube by 12. Y is d by, so 2. So y is d by 2 now. So that's why you will get d cube by 6 sigma. So you feel that this is the right, but exactly this is the meaning. Inner meaning is this. How it's balance the moment. How it is balance the moment. How it is the carrying capacity of the section is like this. This is the idea. Okay. So compressive force, tensile force. Okay. This is just a formula. PDQ by 6. So this is out of topic. You already know it is in strength of metals, but I will give again idea. So this is idea. So up to yield stress, we feel that it has a capacity of yield stress only. We will take it as a we will take as a sigma y is the last point. So that's why up to sigma y we'll take it as. Later, what is the carrying capacity of the section? So carrying capacity of the section, you will get it and find out the moment carrying capacity. It's something is 50. Something you taken as a 50. So if you applied a 100, so if you applied a 50 moment here, 50 moment here, it reaches maximum value. If you applied a 60, we taken as a failure. We don't design a section greater than 50, because the carrying capacity of the section is 50. So we will design like means maximum possible moment acting at the section is 50 only. We will design like this. Okay, that's not a problem. That's not a situation here. The situation is here. If you applied a 60, what will happen? In general, we'll taken as a failure, but the section is failure really going to failure? No, it's not going to be failure because it has a strength. It has a hidden strength of this much of whole strength is there. It much of whole strength is there. So what will happen? What will happen? So what will happen? See. What will happen? See this maximum section. So if it increase, if you applied a greater than that carrying capacity, the strain will increase the elastic strain will increase. Are understood? Strain will increase. The stress is same. So stress is same. Sir, how it is increasing the carrying capacity, sir? If it is increased the 60 also, it will sustain. How it is sustained? It should be produced 60. It will should be produce a 60 moment to counteract that 60. How it is produced? That is the question. So strain is increasing, but the stress is same. The stress is same at the outermost edge. But see, that's a basic question is, the basic answer is, the edge fiber is reaching the Fy, okay. But the remaining portion, see this layer, that means this layer, this layers, edge layer will reach its maximum yielding capacity. But inside of those layers, presently they didn't reach that limit. It has a capacity. It's somewhere here. Remaining fibers are somewhere here, not reaching yield capacity. Only the edge fiber reaches the yielding capacity. So if you increase again the load, the strain for the edge fiber, strain is increasing. The stress is same, but it doesn't reach failure. Because see, failure point is somewhere Somewhere here it doesn't failure, but the remaining fibers in the section will increase, now it is increasing. Are understood? So now what will happen? The next fiber, the top fiber is greater than ey, the next fiber reaches to ey. So exactly the next fiber will reaches to the Young's model. So elastic strain. Are understood? So based on that, next fiber reaches the elastic strain, next fiber gets the elastic stress. So that means what? Next fiber is elastic stress. Same thing, same stress, same stress. Again, if you increase the again the load, so the next fiber reaches to the elastic strain, next fiber reaches the elastic strain. So elastic stress, that reaches to elastic stress. That's why that's increase. If you applied 80, if you applied 80, outermost edges, certain edges reaches to the elastic strain. See, this is elastic strain, elastic stress, this is elastic stress. Outermost edges all reaches to the elastic stresses. This stress or this force we didn't consider in the elastic analysis, but plastic analysis we consider this stress also. That is the idea, that is the ultimate strength analysis. We will consider this strength also. So again, if you increase the load, what will happen? Again increase the load, what will happen? Up to the failure of the section. Where will get failure? So up to all sections reaches to the sir, understood? All sections reaches to the elastic strain. All sections reach to the elastic strain. So this is Fy, this is Fy. Now if you consider what is the section capacity, sir, what is the section capacity of the total in plastic analysis? This is an elastic section capacity, elastic analysis section capacity. Now you see, this is the real, not an ideal, this is a total capacity of the section. So now if you see, this is a compressive force, this is a tensile force, this is a lever arm. If you take in this moment carrying capacity, CRT multiply with lever arm. So that is the moment carrying capacity of plastic analysis. So if you see, this is a plastic range. If you observe it, this total range, ductile range, strain hardening range, this total range we consider as a plastic range. So otherwise I will write here, this total range, it call it as a plastic range. We take it as a plastic zone. It will stretch it. There is no increase of stress, but the strain is increasing. That is called a plastic. It's a plastic behavior. Na? So this is class plastic analysis. Plastic moment carrying capacity. Plastic moment, not elastic moment carrying capacity. Plastic moment carrying capacity. That's why we call it as MP. This is called ME. So what is this value? This value will say it's. We will see it is. Okay. So that is the analysis of plastic analysis. Are understood? That is the plastic analysis. Okay. If you see the moment curvature curves, what is the curvature? And again I will ask, what is the curvature? Curvature is, this is the curvature. That is the curvature. So if you take in this is a curvature, so maybe you seen somewhere like this. If it is section is there, it is, if it is bending like this, you may feel that this is the curvature. That is the curvature. Both are same. Okay. So this is the curvature. How? Okay. If you see, this is the elastic curvature. This is E5. So what is this curvature? Now it is the curvature. If you see, now once increasing, this is exactly, this is a, okay, this is a elastic curvature when, so okay, this is a stress diagram na? So okay, remove it. This is a elastic curvature. Elastic curvature is strain divided by d by 2. That's the strain divided by, this is d by 2 na? This distance, the distance is not an exactly d by 2. If you take an irregular I shape, it is somewhere, so I didn't mention it's a d by 2, so that is a t dash. I call it as a, I call it as t dash something. That is a strain. If you observe it, if you increase the load, if you increase the load, the curvature, the edges will happen. What will happen? The edges reaches to more strain, more strain. The later, the first part also, see the part and the section G, this part also reaches to elastic strain. This part also reaches to elastic strain. So what is the curvature? At the end of the plastic analysis, what is the curvature? So curvature is like, exactly if you taken like this will section, later section also reaches exactly, it's a pi by 2, it's a 90 na? See, it will increase, it will increase like the stress diagram. See, this is 90, you can feel that is a strain diagram also. So otherwise if you see, this is a strain, this is now if you taken as a elastic strain. So because these are all reaches to, these are all crossing somewhere, so if you go to, this is a elastic strain, if you applied again load, this elastic strain is increasing, it reaches to 90 degrees. Are understood? So that is a moment curvature diagram. Otherwise I will draw a moment curvature diagram. Moment curvature diagram. So up to small, it's a moment, it's a curvature. Curvature is, again I will say, this is a curvature. So this is a strain in compression region. This is a strain in a tension region. If you take it is, because if you take an irregular I shape, both are different. Sir, which one is considered, top or bottom? If you take an irregular I section, that's why for the problem, elastic strain at compression, strain at tension divided by total depth. That is called as curvature. That is called a curvature. Don't take top, don't take bottom. So take in both consideration. I just explained for the rectangular section, that's why I give top. Okay, both are same. If you take an up to the low moment is applied, very small moment, up to certain moment, it is a proportionality. If you applied a moment, it will reach us to, see, for small load, it is a stress strain diagram. For again, if you applied load, it is a stress strain diagram. Because the stress strains are proportionality. Up to proportional limits is small increasing. Up to proportional limit, what will happen? Strain is increasing with respect to the stress, with respect to the applied load. It's proportionality. So up to the yield point, it is exactly proportionality. Very small proportionality. That's not proportionally increasing the strain. So that's why it is increasing like this. Later it will cross the proportional limit, strains will abruptly increasing. Are understood? Once it crosses this elastic limit, the strains will easily increasing. There is no increment of stress also, it is automatically, it will increase. Very small force, it leads large strain. Okay, so that's it. It will go like this, it will go like this. At the end of the plastic analysis, at the end of the failure point, there is no increment of the moment is required. The stress, the point, the section is look like maida. If you just press it, is easily shifted to maida. So if you taken a steel bar, if you just applied it gives some resistance. But if you took aluminum, it will easily bend it. Again it will go so many malleable material. Some materials are there, so not only spring, some plastic materials you can observe it. If you just hold it, it will easily shrink it. Take a tennis ball, not a tennis ball, very low tennis ball, just it will give any shape. I understood. So the plastic total section capacity is reaching at that section. This is the moment. So no need to increase moment. So curvature is going on. This is the moment. This is called moment carrying capacity of the section in plastic analysis. This is going to be, if you see, this is the moment carrying capacity of the elastic section analysis. This is the curvature. This is the curvature. It's going on. It's going on infinite. No need of increased moment. It will going on. So this is a pi by 2, I think. Pi by 2. Later it will go infinity. So some textbooks they call it as a pi by 2. Some section it is say that it's infinite radius of curvature. Infinite radius of the curvature. If you just see, if it is there, it will give some deflection. You feel that this is the radius. If you again increasing, it will go like a rotation. It will go like a rotation. It will give any shape. Okay, it will. So just bend it. It will give. Okay, so it's like a plastic. This is a moment carrying capacity in the section of plastic. This is the elastic moment carrying capacity. So this is a just a basic idea. What is the moment carrying capacity? Now if you see, what is the moment carrying capacity of this section in a plastic analysis, sir? So in a elastic analysis, we already developed it. What is that? What is that? M is sigma in multiply with Z. Z is I by Y. So this is Z section modulus. Section modulus. We call it as a section modulus. Okay. Elastic section modulus. We call it as a elastic section modulus. So for plastic analysis, what is the moment carrying capacity, sir? Plus plastic moment, what is the moment carrying capacity, sir? Okay. So now you can observe this tensile force, this compressive force should be equal. That maintains equilibrium. So if you see the stress, stress is same. Stress is same to exactly see what is C. What is C? Stress multiply with area. Stress multiply with area. Na? So what is compressive force? Tensile force. Again stress multiply with area of this region. Okay. So compulsory C and T compulsory should be equal. The stresses are same. So compulsory areas are equal. Areas are equal. Sir, what is that meaning? So the tensile area and the compression area should be equal. So the nodal axis is changing. Previously, it is a center of gravity, not an equal area axis. Center of gravity axis. But now it says equal area axis. The nodal axis will change. Sir, how it is changed? How it is changed? So that's we'll discuss later how to find out the moment carrying capacity in a plastic analysis. So one thing I missed it. See, we will consider only for elastic loading or elastic behavior of the material. We will call it as elastic material or elastic analysis. We will consider totally plastic analysis. We will consider total strength. That is called plastic analysis or plastic materials. Plastic analysis, plastic material. If we utilize certain part of the elastic loading, certain part of the plastic loading, not a loading, plastic behavior, we utilize, if we utilize certain part of the elastic loading, elastic behavior, certain part of the plastic analysis, plastic behavior, we call it as a elastoplastic material. Okay, elastoplastic material or behavior, anything. Elastoplastic analysis also. If you consider that is analysis, this is elastoplastic analysis. Elastoplastic analysis. Okay, that is a plastic, this is elastic, in between elastoplastic analysis. Okay, so how to find out the moment carrying capacity, what is exactly plastic hinge, we will discuss later. Okay, that's the end of the class. Total class brief. What is the brief? So the material has so much strength after the yield point. The material has a strength after the yield point also. If you consider the strength after the yield point also, what is the moment, what is the carrying capacity of the section? That is the only thing we learn it. Okay, the material has a capacity later yield point also. If you consider that is also a strength of that material, what is the capacity of that material or any section, maybe in axially or bending or flexurally, anything, axially or flexurally, what is that section, what is that capacity? That is the plastic analysis. Okay, we can call it as ultimate strength also, ultimate strength, ultimate analysis also. Okay, these are more probably you can discuss more in next semester RCC, reinforced concrete analysis, they will discuss extensively, but we discussed very good, I think. Okay, so that's it, today's class is that's enough. So tomorrow we will see what is the plastic hinge and the plastic moment carrying capacity of the plastic section. Okay, so that's enough today's class, and